gate level minimization or Karnaugh map, and then we'll do the lab. Everyone sees the screen?
Yeah.
Okay, good. So what is Karnaugh map? A Karnaugh map is a graphical technique used for simplifying Boolean expression. It is a matrix consisting of rows and columns that represent the output values of the Boolean function. So it is a graphical approach. We can use it for simplifying the Boolean expression. We mentioned one approach before to simplify this Boolean expression using Boolean algebra. So like if we have x plus x, so this equal to x, or we have repetition for terms or product terms, so we can take only one and skip the rest of repeated term. So we used before Boolean algebra to simplify the Boolean expression, and we mentioned why simplifying the expression or the Boolean function, the output Boolean function, either y or f, or whatever you call it, why it is important, why simplification is important. Anyone can tell me, please, why we need to simplify what we get for Boolean expression? Why?
To reduce the amount of material you have to use in your circuit, like the amount of gates that you use in a circuit.
Exactly. Thank you. What's your code, sir?
30.
30. Okay. Thank you, James. Exactly. We need, when we put the design and when we get the Boolean expression, the more simplified we can get, the more saving of number of gates we use. And of course, we mentioned this save money, of course, with larger systems, and save time also when we do maintenance for this system. So simplification is critical issue in digital design. So we did examples before for how we do simplification using Boolean algebra. Now we will use another technique. It's a graphical technique. It's called the Karnaugh map. Actually, Karnaugh map, if you put the map well organized, as we will see how, you get the maximum simplification directly. When you get the result, this gives you the maximum simplification you can get, which is perfect because this saves like mathematical Boolean steps to get simplification. As we will see how this happens. So the sum of min terms for n binary variables we have here in Karnaugh map, we have another terminology called the min terms, or the number of the squares in the Karnaugh map. It's called the min terms. So if we have n variables like inputs, so this gives us 2 to the power n min terms. The number of min terms will be 2 to the power n, or the number of squares. So for example, if n is 3, the number of inputs or variables, or the number of bits, 3. So this gives us 2 to the power 3 equal 8 min terms. For example, given the truth table here, as you see, and we can see here the inputs ABC. And please, when you write the truth table and use it for Karnaugh map, you must put the inputs, or you write the inputs in the table in this order: A, B, C. Start with A, then B, then C. Then we have 3, so this means the 2 to the power 3 or 8 unique combinations, which if I need to write the inputs here, the different combinations. So I start under C, I start 0, 1, 0, 1, 0, 1, 0, 1. Then repeat the numbers. So 0, double zeros, 0, 0, 1 double ones, then 0 double zeros, 1 double ones. Then again, we have 0, 0, double the numbers. So 0, 0, 0, 0, from 2 to 4, of course. 1, 1, double, 1, 1, 1, 1. If you look at any state or any combination here, never you see the same combination in this table. Every combination is different than the other one. Then we can see here F, or the fundamental products, or the product terms, all are the same. We have 1 here, 0, 0, 1, 0, 0, 1, 1. This means this is the output we get for this input. So if the 3 inputs are zeros, A0, B0, C0, so the output would be 1 in the system or the circuit. A, B, C is the inputs, F is the out, and we have circuit. So for inputs 0, 0, 0, the output is 1. For inputs 1, 0, 0, the output is 0. I read from left to right. Least significant bit at C to M, most significant bit at A. Next combination 0, 1, 0. The output is 0. 1, 1, 0. The output is 0. So F represents the output, F or Y, as I mentioned, or any other variable you use, any other symbol you use. So this F represents the output. Then you can see min terms here. Min terms. Min terms is related to, again, how many bits at the input, how many variables at the input. We mentioned 3 for this case, so we have 8. 2 to the power 3 is 8. It's also related to the number of different combinations, but in order. We must put it in order. So we start with M0, then M1, M2, M3, M4, M5, M6, M7. So we can see here M0 is 1, M3 is 1, M6 is 1, M7 is 1, and the other min terms are zeros. Okay. Then the product terms. F, as we mentioned, is the output. F represents the output, which is related to the product term 1, right? So all are related to each other. But F represents the symbol at the output, like Y. We use usually Y, but here is F, is okay. And again, it refers also for like fundamental product. The product terms or fundamental products, in this case, you can see to get these products, we look at where F is 1 and put 1 in circles. And again, to put 1 here, so the product term will be A inverted, B inverted, C inverted. we mentioned that the multiplication of these inputs must be 1. So to get 1 here, we have to take A inverted, B inverted, C inverted, because A or B or C is 0. The next one here, so we have the product term is A inverted, B, C. Next one, A, B, C inverted. The last one, A, B, C. So this gives f as a function. As a function, f equal to this, which gives us the sum of the product terms. We again, the example here, we are given the truth table, and we need to get the Boolean function. We need to get the Boolean function. So, as we arrange the truth table here, but we add here min terms to see how we represent this f in terms of the min terms. But so far, the product terms we did before, and this expression we got it here, we did like this before. And definitely, when we got the f here, these are standard terms or not standard terms?
Standard. Because you see all the variables.
Perfect. What's your code, sir?
7.
Okay, perfect. Thank you. Thank you, Chen. Thank you. Of course, these are standard terms. We have all variables as Chen mentioned. We have the variables are ABC. So we have all the terms here in all variables in each term. Now, to express this Boolean function in terms of min terms, again, f is the Boolean function. So the first product term is corresponding to M0. The next one corresponding to M3. The next one corresponding to M6. The next one corresponding to M7. So f in terms of the min terms equal to M0 plus M3 plus M6 plus M7. This will lead us to get f as a function of, as the sum of min terms. So this equal to sum, this sigma, this symbol is called the sigma or sum. 0, which related to M0, which means refer to M0, comma 3, which refers to M3, 6, which refers to M6, 7, which refers to M7. So this expression, the formal expression for Boolean function in terms of min terms. And this most likely, which we will be given when we do Karnaugh map. If we are given f, we most likely we will be given f in terms of the min terms, like this. So we have to understand when we have the f equal to sum of these numbers, like this. So what this means? 0 means M0. 3 means M3, 6 means M6, 7 means M7. Again, what does this mean? Again, this means again the function at M0 is 1. The function, the Boolean function at M0 is 1. At M3 is 1, which is given here. At M6 is 1, at M7 is 1, and the rest are zeros. Okay. Now, how we arrange the Karnaugh map? Karnaugh map has different categories. Either we have 4 squares like this, or if we have 2 inputs or 2 variables, x and y. If we have 3 inputs like x and y and z, so 2 to the power 3 is 8. So we have 8 squares like this. If we have 4 inputs, x and y and z and w, or whatever variables you call, meaning 4 variables, so 2 to the power 4 is 16. So we have 16 squares. I don't have it here. We'll talk about it next time. Okay, so we have either 4 or 8 or 16. How we arrange the 4 if we have 4 squares? This standard form, these are standard forms we must keep in mind. Okay, so we have 2 inputs, x and y, or a and b, or whatever. So let us say x and y. So 2 variables, or 2 inputs, or 2 bits. So 2 to the power 2 is 4. So the number of squares are 4. Then we write it like this, and we put here x, here, and y in the same arrangement to avoid any confusion. Then x either 0 or 1, y 0 or 1. So based on the arrangement of these squares, so this M0, M1, and of course M0 for inputs 0, 0, M1 for inputs 0, 1, then M2, then M3. So even like the numbers, 0, 0, M0, 1, 0, if we read correctly from right to left, 1, 0 means 1. So this M1. 0, 1 means 2, M2. 1, 1 means 3, M3. But you don't have to do this every time. Of course not. Arrange correctly, like you put 0 here, 1 here for x, 0 here, 1 here for y. Then in sequence, M0, M1, M2, M3. Okay. After we draw the Karnaugh map like this, whatever we have, 4 squares, 8 squares, 16 squares, and there are values inside based on corresponding to the value of M0 or M1, M2, M3, like we have 1 here, 0, 0, 1 inside the box. We have to group the ones. Please listen carefully, okay? Because this is how we use the Karnaugh map. And if it is clear for you here, it will just take few minutes at home to review. After we put the ones, or after we fill out the table, I mean the map, we need to group adjacent ones. So the criteria of grouping, we look first for 8 ones, 8 adjacent ones. This is the best grouping for best simplification. Our purpose to get maximum simplification in the expression of f or y. So grouping adjacent ones, this is first priority. But if we don't have 8 ones adjacent, so we look at 4. The next category, 4. If we don't have 4, we look at 2. Then 1 is the last option, is the last category. If we have individual 1, we just take this individual 1. But if this individual 1 can be grouped with another ones, even the other ones are already taken into other groups, it will be fine, it will be great. because this again simplify the expression as we will discuss. So now this good example here, this good example, and please do these examples again at home from A to Z. Okay? This good example here. We are given the truth table. And of course, from the truth table, we mentioned we can get F or the Boolean function. So given this truth table, and we need to simplify the Boolean function. So here we will use the two approaches we mentioned so far. We'll do simplification after we get the expression using the Boolean algebra. And we will use Karnaugh map to see what we get at the output. Okay? And we mentioned before, if we did that correctly, we must get the maximum minimization in the expression direct. So let us see what happens here. So this is a table. This is a table here, truth table. And given the inputs, we have two variables. So we have four different combinations. 2 to the power 2 is 4, which means also 4 squares or 4 min terms in the Karnaugh map. But let us focus here on this truth table. So we have F is given here. And of course, the corresponding min terms M0, M1, M2, M3. And I put min terms here because we need it for the Karnaugh map, okay? And then we need to get the fundamental products. So we look at ones. We know fundamental product is 1. So we look at ones. Under F, where ones. Put them in circles and get the corresponding product term or fundamental product. So let us say F1. To get 1 here, what is the fundamental product or the product term? Can you tell, please? Can you answer me? For this one here, what is the corresponding product term?
1, 0.
1, 0 is the input variables, but based on 1, 0 or y is 0 and x is y is 1, x is 0. What
Isn't
is
it like X inverse Y?
X
for the first one?
inverted y? Perfect. What's the code?
Tres.
What? 3?
Yes.
Bang?
Yep.
Joshua, thank you, Joshua. Guys, we mentioned the product term is not bits. The product term is variables. Yeah, corresponding the bit 1 and 0, but what this means? This means we have x is 0 and y is 1. So we take x inverted multiplied by y for this product term. Okay, the same guy who mentioned 1, 0. Now, what is the product term for the next one? Can you tell me, please? For this one, what is the corresponding product term?
X inverse Y.
X inverse Y or XY inverted. Okay, now what's your code number?
30.
3, Joshua?
30.
Oh, 30. Okay.
I mean, I'll take it.
Not now. Okay, thank you. Thank you, James. Okay. The next one. The next one. What is the next one? The last one. What is
XY.
XY.
XY? Perfect. Now I am happy to hear many. Okay, thank you. The last one, XY. So simply now the function is the sum of these product terms. f1 plus f2 plus f3. F as expression. We have f here as a value, but we need it as expression. Why we need it as expression? Why do you think? Double points for anyone answer me. Why we need the expression? We have the values here, but the purpose to give the expression based on what are given here. But why we need to give the expression?
Because X
Because
is
of
atomic.
Agree the circuit.
Exactly. To draw the
Because we
circuit.
can,
Who
yeah.
says the circuit? Who says the circuit?
Number 10.
10? Arthur, thank you. Perfect, thank you. To draw the circuit. Because the design needs to draw the circuit. To create the prototype. Do the circuit, check the functions, verify the functions, like by measurements, like we put a LED and, you know, we see, like in the lab, we mentioned the measured. So this verifies the function. Or this is a verification for the function of the circuit. So we need the exhibition to draw the circuit. And as we mentioned, to draw the circuit, we need maximum simplification to reduce the number of gates. If I can use, say, 3 gates to get the function, full function, why I use 5 or 6 gates, you know? So we got the expression here as we get from the f1, f2, f3, we add them up. So we got x inverted y plus xy inverted plus xy. Most likely, the expression we get directly from the truth table most likely needs simplification. Because, why? Because when we get the fundamental function, the f function, which is the sum of the fundamental products or product terms, we get them in standard form, which usually can be simplified. So as we see here, this is the expression here, so we can copy x inverted y plus, look at this term, these 2 terms here. Can we simplify these 2 terms based on Boolean mathematics? Boolean algebra we
You
use?
can factor out x and then y inverse plus y is equal to 1, I think. No, 0,
Perfect.
0.
Yes,
Wait.
of course, 1. What's your
Okay.
code? What's your code?
The number after 2.
2 or 3?
3.
Okay, bang. Number after 2. That's good exhibition. Okay. Please, we need more participation, guys. Still same people, most likely. So please, we need more participation. Be with us, okay? It's good discussion. So this exactly, we can see here x is common. xy inverted plus xy, we can take x common. Especially we have y inverted here and y. So x common, so multiplied by y inverted plus y. If you go back to Boolean algebra, you will see y inverted plus y is 1. We know that now. So x times 1 is x. X times 1 is x. So if x is 0, 0 times 1 will be 0. If x is 1, so 1 times 1 will be 1. So x times 1 is always x, not 1. Not 1. Because simply if x is 0, this doesn't equal 1. So x times 1 is x. So we have x inverted y plus x. Does this remind us with certain expression before? Yes, remind us with x plus x inverted y. Or a plus a inverted b, which equal to x plus y. I put it here aside also to remind you how we got x plus y. So we mentioned x plus x inverted y we can put x as x plus xy. It's the same. Plus x inverted y, then is x, plus we can take y common here, multiplied by x plus x inverted, which is 1. So y times 1 is y, so this equal to x plus y. This is good. I mean, we did that before as a rule of Boolean algebra. X plus x inverted y equal x plus y. But if you forget the rule, you can prove it. You can get it. You can get it from here. Okay. So this is the approach we used before. This is the approach we used before. We have the truth table. We are given the truth table. Of course, truth table has everything like the input variables, the value of f. So we need to get the product terms, which we did here. To get the product terms, we look at ones where f equal to 1 and put ones in the circle. In circles to just highlight. Then get the product term corresponding to each one. F1, f equal to 1. So like we did for this, the first one here, this f1 equal x inverted y. And the second one and the third one. Then we add them up as output function, f. So we add them up. Now we look at how to simplify this expression. Simplified up to f equal to x plus y. You see how the expression looks like at the beginning? Now this means more gates, more inputs, but now we got just x plus y. Just OR circuit. Because this sum of product, we have logic addition here. So the output is OR circuit with two inputs x and y. That's all. Now let us how we get this using a Karnaugh map. Again, we draw the standard Karnaugh map for two functions, for two inputs, x and y. So we put 0, 1, 0, 1. Then inside the boxes, M0, M1, M2, M3 in order. And we look at where it's better to most likely, it's better to look at where M equal to 1. You don't have to go in front of each min-term. Most likely, the ones are less numbers in the output function. So we look at where M are ones. Like here, M1 is 1, so we put 1 inside the box. M2 is 1, we put 1 at M2. M3 is 1. So we put all ones, we are sure we put all ones. Then the rest of the Karnaugh map put zeros. Of course, this case is different because we have only 1 0 and the rest are ones. Of course, you can choose to put M0 is 0 and then the rest are ones. But what I mentioned, most likely the number of ones are less. So you may choose where the min-terms are ones and put it, fill out the Karnaugh map with ones, and the rest will be 0. We always looking to also save our time, you know. So this relatively save some time, okay? Now, the second step, or the step after that, we group the ones before we do anything, before we solving the Karnaugh map or get the function. We group ones. We mention what is the best grouping first? How many number of adjacent ones?
A, 4,
A.
2, yeah.
A, you see 8. Who said 8? What's
5, 7.
7? Okay.
Someone else also did. Yeah.
What else? What else?
28.
And who else? Okay. 8. Start looking for 8. If we don't have 8, we look for 4. We look for 4. Then 2, then 1. So of course we don't have 8 here because this simple Carnot map, we have just 2 variables. So we don't have 8. Do we have 4 adjacent ones? No. But we have 2. We have 2 here. We have 2 here. But we have 2. I mean, we can get 2 in one group. Okay. So we have 1 here. Please follow with me. We have 1 here, 1 here, and 1 here. So one may say, I will take these 2 ones in one group. Okay. So what is left? What is left after we take these 2 ones in one group? What is left?
M2.
Take the bottom.
We have 3 ones here. We took these 2 ones, adjacent ones, in one group. What is left?
M2.
M2
and M3.
One left, only 1 at M2. At M2, right? Oh, I'm talking about ones. I am talking about ones. So we have, in this case, we have 1 left in M2. Okay. One may say, oh, so I take this one in one group, just 1 in one group. This is not good. Why? Because we mentioned, as much we can simplify, we do it. So since 1 here in M2, and we have adjacent 1 in M3, so we can take them in one group too. One may say, oh, we got 1 in the 1 in M3, we already put it in one group. It doesn't matter. It's okay. So just add this one to another group with M3. This will gives us more simplification. Everyone see this or not? I can repeat if you don't see it. Despite we took already the 1 in M3 in a group with M1, we can still take the 1 in M2 as a group with M3. Okay? Now, how we get the product terms? We need the product terms because we know f at the end, the function equal to the sum of the product terms. So we need to get the product terms. How we get the product term? The product term is using the Carnot map. Let us say this is F1, the first product term. How we get F1? This group inside a big square here. So look at the big square which covers the whole group. Okay? Okay? Now look at this direction. Look in this direction towards the variable x. What we have here in front of this box, x equal to what? 1. Perfect. So we take x in this product term. So F1 equal to x. And we can multiply with other variables if it is valid. Okay. Before we leave this part, if x here is 0, if x, you see the cursor? You see the cursor?
Yes.
X here is 1, so we got x. But if x is 0, so what we take here? X not perfect. Thank you, sir. What's your code? 15. Perfect. Arthur, thank you. Okay. If it is 1, we take it as it is because we need 1. Why? Because 1 when it's multiplied by whatever, it will not be 0, right? Because we have 1. But if it is 0, we must invert it. We take the invert to keep 1. Okay, so we're done with this direction. Now, we look at this direction here within the whole box of the group. The group, we put it in a box which covers the whole group. Then we look at the direction of X variable, horizontal direction, in this case. Then we look at the corresponding variable in the vertical direction within the box, the whole box. So the whole box is here, right? So we look vertical. So what we have for Y? What values of Y within this box? What we have?
1.
Just 1?
Oh, 1 is 0, but 1 would give
1 and 0, right? We have 0 and 1, or 1 and 0. So this means Y within this box or within this group has 2 different values, 0 and 1. Because it has 2 different values, so we skip. We skip Y. We don't take it because it has different value. We can't take 0, or we can't consider 0, so we can like take Y inverted, or we also can't consider 1, so we take it Y. So should we take it Y inverted or Y? We can. So we skip. Okay. In the process of this Karnaugh map, if we have the variable has more than 1 value and the different values like 0 and 1 or 1 and 0, we skip this variable. But if we have, say assume Y is 1 and 1, should we take it? Should we consider Y in the fundamental product or not? If it is 1 and 1, assuming Y here is 1 and here is 1, should we take it or we skip it?
We should take it.
Take it. Okay. Who agree with take it?
I
Who
did.
agree?
I
I did. 7.
I agree.
I agree
Oh,
too.
okay,
I do.
good. So who said we take it?
7.
7. The same people, guys. Okay, thank you, Chin.
I think other people also said it.
Who?
3-0.
3-0. Okay. Anyone else?
28.
28. Good. Same people. Anyone else?
18.
Anyone not mentioned anything before?
Someone said 18.
18? No, 18 has already bonus credits before. I wish to hear someone not mention anything so far. There are some of our friends never participated before. I don't want to mention names. I mention the names for the people who has maximum participation. But please, everyone try, okay? So if it is 1-1, we take it. And we take it as Y or Y inverted?
As Y.
As Y. Perfect. Thank you, sir. But if it is 0-0, assume 0-0. This is one variable. So we consider Y in the fundamental product. But in this case, we take it Y or Y inverted? What do you think? If Y, assuming Y here, 0 and 0. So this one variable, not 2. and the same variable. But in this case, we take y or y inverted. Y inverted. Perfect.
Why you very
Okay, thank you, Hadi. Thank you. Okay. We take y inverted. Okay. So let me summarize what we mentioned in this part. We put the group in one box. And then we look at the variables in front of this box. The different variables. So we, because we have variables in this direction, and vertically because we have other variables. Especially when we have more than two variables. So we look like we look for the x variable in general. But now, if we have one value for x in front of this box, so we look at what is the value of this x. If it is 1, we take it as it is. If it is 0, we take x inverted, or the variable inverted. If we have two different values for the variable in front of this box, two different values like 0 and 1 or 1 and 0, so we skip this variable. We consider it if it has two variables but the same. Like here y, for example, we have instead of 0, 1, 0, 1, and we skip it, but 0, 0, we take it as y inverted, or 1, 1, we take it as y. Okay? Is this clear, guys? So if 1 here is just equal to x. Now look at the other group, which is this group here, F2. Again, we put the group, the whole group in one box here. One box includes the whole group. And we look again horizontally towards x variable. So what we have for x in front of this box? Do we have one variable, the one value or two values for x?
2.
2, perfect. From here to here, we have 2. These two are different or the same? The two values are different or the same value?
Different.
Different. So what we do for x?
Skip.
Skip. Perfect. What's your code, sir?
7.
7. Okay. Please, all other people agree with this? You see this? You see this or not? You see this or not? Please tell me if you have question. But don't be silent. If silent, I don't know if you are okay or not. Just tell me. If not, we can repeat. If okay, so we can move forward. So what you see? Again, we mentioned in front of this group, this box here, if we look towards x horizontally, so x has two values, 0 and 1, two different values. So we skip x. Now we look at towards y. Towards y in front of this box. How many values for y in front of this box? How many values for y?
Two.
Y2. Can you tell me what is the two values?
0 and 1.
0 and 1?
Mhm.
What's your code, sir?
27.
27. Minus points. I'm
Okay.
joking, don't worry. Y2, 27. Y2.
Because on
In
top
front
says
of
y.
this box, why two variables you see?
Because y is 0 and 1 and x is 0 and 1.
No, this is not, this what is given in the Carnot map. But I'm talking about in front of this box here. You see the box?
Yeah. Now you're
What
outlining
is
it.
the value here?
1.
Just one, right? You see, guys, when someone discuss, and even if there's something wrong, you see, now he understand well. So that's why I encourage everyone to discuss and participate. Okay, you see 27? You see this one? Only one. Whatever the value, but only one variable here. One value, I mean, one value for y, right?
Alright, I'm following.
Okay. So this value is 1. So what do you think? Should we take 1 or should we take y or y inverted?
Take Y.
We take y because y is 1. We mentioned we take y inverted if this value is 0. We have to take inverted. But it is 1, so we take y. So f2 is just y because the x variable here has 2 values, different values, 0 and 1, so we can't take it. So we add them up, f equal f1 plus f2, so it is x plus 1. So you see how we got x plus y here and how we got x plus y with the other approach. So Karnaugh map gives us the maximum simplification directly. So you don't have to use Boolean algebra here because it's already maximum simplification. You see the difference, guys? But we need both. Do you see the difference or not?
Yep.
I see it. There are just two ways to simplify.
Yeah. If if you see the expression here, which you got, let me say it in different way. If I didn't do the proper organization for the Karnaugh map, like grouping, or say assuming I take this one in M2 individual. If I take M1 individual here, if I didn't put it with M3 in a group, so what is the fundamental product in this case? For this one?
X, and not Y.
Perfect. Thank you, sir. What's your code? Double points. What's your code?
Oh, my code number is 2.
Number what?
2. 2.
2.
Yes.
Okay. Thank you, sir. Thank you. Perfect. You see, guys, I mentioned assuming wrongly. I took this one. I took one group here, and then this one left. I take it in individual group, like consider individual different group. So I take this box only here. So if this is the case, what is the fundamental product for this M2? Go in this direction, so we have x, so f equal to x. Go in this direction, we have y equal to 0, so 0 y inverted. So this box will be x, y inverted. And then I consider f2 equal y. You know, this is in not proper organization. So what happens? We get the expression here for f. Now this f needs more simplification using Boolean algebra. Because we didn't do proper organization for the map, for the Karnaugh map. Okay? Okay. Okay. Okay, let us continue next time because we need to move to the lab. But any questions so far, please? Any question? I hope everyone review this part well before we go before our next class. Just when we continue, you can remember what we mentioned, okay? Any question? Any question so far here?
No.
No questions?
No
Okay.
question.
Okay, thank you. So let us go to the lab. Just 1 second. Everyone see the screen for the lab? You see the screen for the lab? You see
Yes.
lab?
Yes.
The
Yeah.
lab? Okay, good. So this lab about design with multiplexers. So what is a multiplexer? Multiplexer is very important component in general, but especially in digital design. Multiplexer means we have different inputs, and based on another control inputs, we can choose only one input, only one of these inputs to appear at the out. Again, multiplexer, we have inputs and out. Of course, one out, Y or F. As the input, we have different inputs. We have different bits, different variables like X, Y, Z, or A, B, C, whatever. So we have different inputs, different data inputs at the multiplexer, as the input of the multiplexer. And based on another control inputs or selectors, it's called selectors or control inputs, we pick up one of these different inputs, only one, to appear at the out. Only one of these inputs allowed to appear at the out. So we have different categories for multiplexer, like a 4 to 1, like 4 inputs to 1 output, 8 to 1, 16 to 1, 32 to 1. So we can get more complex multiplexers. So this is the main function. Different inputs using selectors or control inputs, we allow only one to appear as out, only one input to appear as out. So for example here, if you look at this here, this is the circuit in gates inside the multiplex. Or let us look at the block diagram first, or the symbol of the multiplexer. This is the symbol for the multiplexer. Max means the multiplexer. 4 by 1. 4 means we have 4 inputs here, and of course 1 out. So the inputs are D0, D1, D2, D3, like 0, 1, 2, 3. Okay? And you see we have control inputs here, 2 control inputs, S0 and S1. It's also called selectors. If we see here, if we have 4 inputs, how many control inputs here? 2, right? Why 2? Because 4 4 inputs equal to what? 2 to the power 2. So we need 2 control inputs here to cover all different combination here. So for example, let us look at here. This is the truth table. S0, S1, the control inputs or selectors. The different combination is 0, 0, 1, 0, 0, 1, 1, 1. So this covers all the inputs. 0, 0 for D0, 1, 0 for D1, 0, 2 for D2, 1, 1 for D3. Like numbers, the corresponding decimal number. For 0, 0 is 0, 1, 0 is 1, 0, 1 is 2, 1, 1 is 3. But here we use the notation of the inputs, D0, D1, because we consider the inputs here or here, D0, D1, D2, D3. Now, if we have 8 inputs here, what is the number of control inputs here?
3.
Perfect, thank you. What's your code?
7.
7. And the other one, please, what's your code? The one who said 2? Yeah. 15? Okay, thank you. So we should have 3 here. If we have 16 inputs, how many selectors here we must use?
4.
4.
Good.
4.
4, good. Tell me your code number. I hope to hear someone new.
19.
17.
90. Oh, okay, good. 19. Perfect. Who else?
17.
And 2.
17. Perfect. And the 2. Thank you. Okay, so based on this is, as I mentioned, the circuit inside. So we have, as we mentioned, we use, most likely in our design, we use sum of product. So the output is OR gate, as you see here. Then based on the inputs and outputs, so we have another 2 OR gates and then AND gates. These are AND gates. And we have the 2 selectors here, or the 2 control inputs connected to inverters. Okay. So, say S0, we apply the bit 0. Okay. The inputs, as I mentioned, D0, D1, D2, D3. Okay. So if we apply at the control inputs, if we apply 0 and 0, 0 and 0, what is the output? What is the input here which appear at the output? If we have 0, 0 here, what is the output? What is the output in terms of the inputs?
0.
0.
Not 0, D0, you mean D0. The inputs are D0, D1, D2, D3. You see, look at the truth table here. So the output will be D0. If D0 is 0, so we will see 0 at the output. If D0 is 1, we will see 1 at the output. You see what I'm saying?
Yeah.
Okay. If the 2 inputs S0 and S1 here is 1, 0, what we should see at the output Y?
D1.
D1, perfect. So now, if D1 is 1, so the output will be 1. If D1, because these data inputs are given. If D1 is 0, we'll see 0. Who said D1?
Number 2.
2, thank you. And so on. If we have 1, 1, this means D3 who appears at the out. And if you follow the circuit here, For example, say we choose S0 is 1 and the S1 is 0. This means D1 will appear at the output. If you follow the inputs based on zeros and ones, you would see the only this gate which gives D1. All other gates will give 0. And this OR gate, so when we add D1 plus 0 is D1. D1 plus 0 is D1. So you will see for D1, this is the only gate gives output D1. The other gates will give you 0. Okay? But you don't have to go through the details now. Just I need you to know, based on the control inputs here, only one input allowed from all these inputs, only one allowed to appear at the output, based on this truth table. Okay? So what this is in general. We put D0, D1, D2, D3 in general. Now for our lab, assume the inputs 0, 1, 0, 1. And remember, where is D0 here? And where is D3? Where is D0 here? Which one D0?
1.
The least significant bit.
What is that?
It's 0. Least significant bit.
Which is 0?
The one on the right.
The first one on the right.
Yes.
So if the inputs D0, D1, D2, D3, so D0 is the least significant bit. I put it here, but you should know even if I didn't mention, because we start, as I mentioned always, we start when we read the binary number, we start from the right to the left. We start from the least significant bit to the most significant bit. Okay? So this means D0 is the first one. Then D1, then D2, D3. Everyone sees this? Okay. So now, what we need to fill out this table? Of course, we need to draw this, as I will show you in the multi-sim. We'll do the circuit, and then we'll measure the outputs based on these control inputs. So for example, here, say for 1 0, say, or 0 1, anyone, say 0 1 here. For 0 1, what is the calculation here? D, give me in general first.
D3.
For 0 1, D2.
D2.
Like the corresponding decimal number, 0 1 is 2. But we talk here about inputs, so is D2. So we put here D2 equal to, D2 equal to what here based on this given?
0.
D0, D1, D2. Perfect, thank you. So we put D2 equal to 0. Who said 0?
17.
17. Thank you, Dylan. Thank you, Dylan. Good. Equal to 0. We put the input as notation first, D2, and then equal to 0. Now measure. We need to measure. So what is the output? What you expect when we measure the output in this case? Which bit appear at the output? What is the value of the bit appears the output? Or which input appear at the output? Which input appear at the output here? Y equal to what?
D2,
D2, and what is D2?
0,
So what you expect is on or off?
off.
Off.
Perfect. So we have to put off here. So everyone, especially the coordinators of the groups, you see what we need to do here?
Yes.
Any question, please? Who said off for the output?
7,
7. Okay.
and someone else also said it.
Yeah.
28. 28.
8?
28.
28. Okay, Stephen, thank you. Okay. Now let us look at any question with the lab. Any question with the lab? Okay.
I don't see the
Yeah,
assignment.
Hmm? What's that?
I don't see the lab assignment. Is that because you'll put it up later or
Oh,
like in Canvas?
okay, I am sorry. Yeah, I will post it. I will post it.
Oh,
Okay.
okay, thank you.
Yeah. Immediately after we finish this, okay? Okay, let us yeah, I forgot. I'm sorry. Let us look at the circuit here. Everyone sees multi-set?
Yeah.
Yep.
Okay. You see, this is the IC. This is the IC for the multiplexer. The number is actually, the number is here. 74153. 74153 for 4-to-1 multiplexer. So this is the actually IC. The actual IC 74 number 74153. Okay, so we pick up oh, okay. So we, like we did before, we choose this IC number, and so what you see here in this IC, you see the inputs here. What is the inputs you read? Everyone sees this? Guys, what is the inputs you read here? One C0, one C1, one C2, one C3, right? This is
Yes.
4 inputs, like we mentioned. We have 4 inputs for this multiplexer, right? What do you see else?
2C0, 2C1, 2C, 2C.
Exactly. So what this means? This multiplexer or this IC
This is
have
2 multiplexers, right?
perfect. Thank you. This is what I mean from my question. This IC has 2 multiplexers. Do you remember? Do you remember when we talk about the scale of integration for the ICs? So here we have inside this IC. What's your code, sir? The last one.
Who, me?
Yeah, the one who said two multiplexers.
Oh, 3.
3. Thank you. So we expect in one IC you may have more than one multiplexer, okay? So we have 2 here. So we choose one of them as the group of inputs. So we choose the first group, like 1C0 corresponding to what input we have in our lab. 1C0 now is corresponding to which input in our lab?
1C0.
D0?
I'm sorry, what did you say, Professor?
1C0, this input here, what we call it in our lab? What is the corresponding input in our lab?
D0.
D0. We mentioned in our lab in general, we have D0, D1, D2, D3, right? Right?
Yes.
But in this IC, as we see here, the numbers used is 1C0, 1C1, 1C2. So 1C0 is corresponding to D0. You see D0 here? So this corresponding to D0. 1C1 corresponding to
D1.
D1,
1C2,
D2, and D3.
D2, 1C3, D3.
D3.
So we connect each input to a switch, and we know how we drag this switch. We did that before, right? To change the input like 0 or 1, okay? Or to connect to 0 or 1. So who said D0 first? D0. Who said D0?
28.
What is your code?
28.
28?
Yes.
Okay, thank you. Okay. Now, you can see here we have two grounds, 1G, 2G. So one ground for each multiplexer. So since we use the first group as our multiplexer, so we choose 1G, one ground to connect it to the ground. Then, where is S0 and S1 here in this IC? Where is S0 and S1?
Looks like A and B.
A and B, perfect. What's your code, sir?
3.
3. Thank you, sir. Thank you. A and B here. A and B represent S. A and B represent S0 and S1. Okay. So A here, as you see, connected to the switch, and I put S0 here to see this. This corresponding to S0. And B connected to S1. Okay? So all inputs, any input, usually we connect it to a switch to have the option to change the input from 0 to 1 or 1 to 0. Okay? Okay. So, and of course, the output, we can see here 1Y, 2Y. Of course, 1Y is the output for the first multiplexer we choose. 2Y is the second multiplex. So we connect 1Y to the LED to measure the out. This LED, which represent for us verification for the function of the circuit. So now let us assume any case. So what we mentioned, S0 is 0, right? And S1 is 0. So let us connect these two zeros like this. And the inputs are given already. So we have D0 is 0, D1 is 1, D2 is 0, D3 is 1. So it's connected here. These inputs, we don't change. I mean, we connected already, and all the changes we do for the S0 and S1 to pick up whatever we need from the inputs. But these inputs, D1, D0, D1, D2, D3, they are given. So we just connect it and we leave it now. Okay? So now say I need to, when we choose S0, S1, so this means we allow which input to appear as the output? For 0, 0.
D0.
D0. And what is D0 we have?
At the moment.
D0, which is given in the lab. What is the
Okay.
the values are 0, 1, 0, 1, right? So what is
so it's
D0?
0.
It's
Zero.
0. So what you expect for the LED?
Off.
Off.
Be off.
Yes.
Perfect. So assume we choose S0 is 1 and S1 is 0. So if S0 is 1 and S1 is 0, so what is this input which appear at the output?
1.
D1. And what is the value of D1 in our lab?
1.
1.
1. So let us see. We have to turn this. Yeah, okay. So what you see?
It's on.
Let us go back to 0, 0. 0, 0 is off, right? Now 1, 0. So the LED is on, right?
Yes.
Right? Okay, perfect. Please don't forget to when you operate the function, you have to click on this the green arrow to make it active. Okay. Okay, now if we put S0 is 0 and S1 is 1, so what is the input appear at the output? Which input? For 0, 1. Guys, the 0, 1 corresponding to what decimal number? 0, 1. What is the corresponding decimal number for 0, 1?
2.
2. So this means D2. D2 will appear at the output. Okay, D2. What is the value of D2? We choose at
0.
0.
0. So if we do that, so you see, off.
Off.
Now for the last one, D3. So 1, 1. And the D3 is 1. Right? Is 1 is connected to 1 here based on the given. So 1 appeared at the output. Okay. Everyone sees this?
Yep.
Any difficulty for this lab? We know how we get the LED. We know how we drag the IC based on the number. We know how we drag the switches, SDT. And of course, the VCC and the ground. Any question? Any question?
No, I don't think so.
Okay.
No questions.
Oh, someone asked me before how we use how we encrypt the IC or the gates, right? So you wanted to see this or not?
I do.
Okay. So I can show you a simple example for this. Oh, sorry. Just a quick example. So let me just. Okay. Just 1 second, please. Since we spoke about the multiplexer, so just make it very easy now. Okay. You see this circuit here?
Yeah.
Okay. This circuit, this IC here is actually exclusive O. This IC 7486 for exclusive O. If you Google it, you will see this for exclusive O. What is the function? What is the regular function for the exclusive OR?
You produce true when you have 0, 0 and 1, 1.
So for similar inputs, 0 output, right?
Yeah.
So for 0, 0, the output is 0, right? For 1, 1, the output is 0. We see this?
Yep.
For 1, 0, the output is 1, or for 0, 1, the output is 1. So this is the regular This is the regular function for exclusive OR, right? So if say some people steal this IC, for example, or this circuit, and they don't know what is this circuit, so based on the inputs and the output, they can discover what kind of this IC here, or this component, okay? Now, we'll encrypt this IC, and we'll see how the function changes when encrypted. To encrypt this IC, we actually use the multiplexer here. To encrypt this IC, for encryption, we use multiplex, like exactly what we did now in the lab. To see the importance of what you study, okay? It's not just a multiplexer. No, there is a function for that. So we have the multiplexer here. And again, we have two multiplexers actually in this IC. The multiplexer number 74153, as we mentioned. So two multiplexer, we use the first group. And then we have the two control inputs, A and B, or S0 and S1. Okay. And we have 1G and 2G, as I mentioned, by default, the ground or VCC is connected on simulation. But if we are in the physical lab, we must connect it. So 1G, 2G, don't worry about it. Okay. Okay, so the output for the exclusive OR here, the two inputs, 1A and 1B, as you see here, and the output is 1Y. 1Y is the output. The same, so now we use, I show you here the exclusive OR without encryption, or the IC without encryption, and this lower bar is the IC encrypted. So how we encrypt it? We take the output and connect it to the input of multiplex. And based on the control inputs here, as we mentioned, based on the control inputs, we allow only one input to appear at the output. Okay? So, the output here connected to like D0, right? And now the control inputs here represent the key of encryption. These two inputs, control inputs or selectors, represent the key of the encryption. So if we choose the right key, so we can see the output of the exclusive OR, the correct output of the exclusive OR. So based on this connection here, what do you think? Which key we use? Like 0, 0, 0,
0,
0, 0, 0, perfect. So we choose 0, 0. This is the right key for this connection or for this encryption to allow D0, which is the output of the exclusive OR, to appear at the output. So when we choose 0, 0, we see the output here. Now, if you change like 0, 0, the output is 0. 0, 1, the output is 1. 1, 0, the output is 1. 0, 0, the output is 0. So we see the correct function of this exclusive OR because we use the right key. Okay. Now assume we choose the wrong key, like 1, 0. So let us see. You see 1, 0. The output should be 1, right? Or 0, 0, the output should be 0, okay? 1, 0, the output must be 1, but we see 0, which is wrong. 1, 1, the output is 0. Okay? So when we use the wrong key, so we have different outputs. Say if we use 1, 0, the same thing. If you change, not the right function. Okay, wrong function. And so on. So we use here the multiplexer as a tool to encrypt the IC in this way. Of course, this is the simplest example. One may say, oh, this is just the key is two values. No, as we mentioned, multiplexer has 4 inputs, it can be 8 inputs, it can be 16 inputs, it can be 32 inputs. So say for 16, so we will have 4 keys here to be used. And the only one knows what is the right key is the authorized person or the designer, okay? Or the authorized person, whatever, the one who used this circuit, okay? So this just clarifies the idea of how we encrypt ICs. Everyone sees this?
Hey, it makes
Yep.
sense.
Oh,
Thank you.
okay, good. Now let us go back to our lab. Oops. Okay. Okay, so please, we still have some time, so just to go ahead, and if you have any question, let me know, please.
So if we don't have any
when you get
questions,
this, just 1 second, please. When you get a screenshot for the measurement, like 2 screenshots for 2 different cases is okay, but should be different than what I have here. Of course, the inputs will be the same. The inputs for these, because this is already given 0, 1, 0, 1, so the connection of the inputs will be the same in any screenshot, but the difference will be in S0 and S1. Okay, so you should give me different, like a different combination, okay, than this one. Give me just 2 examples, 2 screenshots for the 2 different combinations. Okay, yes, sir, go ahead. Someone has question, I think?
oh, I was just saying, so you'll post the lab directly after the class and then we can work on the lab packet.
Yes, sir, just.
Perfect. Is there anything else for today's classwork section of this?
No, that's all.
Okay. Have a wonderful afternoon. Thank you.
You too. Thank you, everyone.
See you, Professor.
Thank you, Professor.
Thank you.
Thank you,
Have a good day.
Professor.
Take care. Bye.
Thank you.
If you can leave if you already okay. Okay. We're almost done. Okay.